In subtopic 5.1 on electric fields, we were looking at electrostatic forces and the electrostatic field that goes along with that. In this subtopic 6.2 on gravitation, we're going to look at gravitational fields. So just as there is an electrostatic force between charges, we have a similar force that we can talk about to do with masses. So with electrostatic force, we're looking at the force that exists between two charges. We'd need to know how much charge there is, the distance apart that they are. With gravitational force, we're looking at the mass that's involved. So with gravitational force, it's a force between two masses. And so similarly with charges, to describe the region around a charged particle, we used electric fields. So you'll recall there that with an electric field we had field lines that represented the direction of force, and the spacing of the field lines represented the strength of that force. We have a similar idea. We can refer to gravitational fields around a mass. So there are very clear similarities between these two types of fields. Fields there. And the representation very much looks the same. So if you think about a mass, so something like the Earth for example, so if we have the Earth with some large mass, the gravitational field is always going to be directed in towards that mass. So one of the key differences between electric fields and magnetic fields, electric fields and gravitational fields, is that you don't have a sort of a negative. So you'll notice that is very similar to the charge, to a negative charge. The electric field around a negative charge, you wouldn't have a gravitational field that pushes away from a mass. So in the same way that we have certain quantities that are represented by an electric field, gravitational field lines are used to show a few different things. So the first is that they show the direction of force that would act on a mass if it was placed in that region. So direction of force on a mass if placed in that region. And the second thing is that the spacing of the field lines, and again this is similar to electric fields, so the spacing of the field lines represents the strength of the force. And those ideas are similar for all fields. The only difference really, strength of force, the only difference is what it is that's causing the field, whether it's charges in electric field, masses in gravitational fields, or magnetic poles in magnetic fields, or currents producing a magnetic field. Now, just as there are a few different ways of calculating the electric field strength, there are a couple of different ways to consider gravitational field strength as well. The first and the simplest way is simply to consider basically the definition that we've just jotted down. Gravitational field strength using the symbol G here is given simply by considering the force that's acting. So gravitational field strength is just the force that's acting on an object due to gravity divided by the mass of that object. And that's an equation that is in the data booklet. So I'll just highlight that quickly. And a couple of things to note here. You'll already have hopefully observed the first one. Since that force is a vector, and we're just dividing by a scalar quantity in mass, then it makes sense that gravitational field strength is also a vector. And secondly, the units of gravitational field strength. If we go back to this equation, units of force are in newtons, and we're dividing by kilograms, so the units of gravitational field strength are newtons per kilogram. Now I just want to, that value of g, the lowercase g, there's a potential area of confusion here, and that is that that we use the value of g. So we've got this value of g as being equal to 9.81 meters per second squared on the surface of the Earth. So what that really means is that we're saying that it's the gravitational acceleration on Earth's surface. So it's really important to note here that this reference point is only specific to Earth's surface. So if we were to go higher than Earth's surface, that value of g will no longer be 9.81. It will change, and the way that it changes we'll have a look at in videos to come. But keep in mind that from Newton's second law we can rearrange that equation, F equals ma, to get that the acceleration is equal to force over mass. So basically what we're saying here is that we've got this a is equal to F on m, we've also got lowercase g, little g is equal to F on m. We're saying that g is acceleration due to gravity, but we're also saying that it's gravitational field strength. So both of those two terms, gravitational acceleration and gravitational field strength, are basically interchangeable. So gravitational acceleration is interchangeable with gravitational field strength. And as we've said, on Earth that value is 9.81 meters per second squared, but considering that we're also saying it's the same as gravitational field strength, it would then also be 9.81 newtons per kilogram. Just to really drive that point home, if we think about the units of newtons per kilogram, from Newton's second law we know that 1 newton is, well, the force is equal to mass times acceleration, so 1 newton, the units of force, are the units of mass, so units of mass being kilograms, and units of acceleration being meters per second squared. So that's effectively what 1 newton is equal to. So there's newtons per kilogram. So you'll notice now we've got kilograms and per kilogram, so they'll cancel, and so we're left with meters per second squared. So the units of gravitational field strength are interchangeable with the units of gravitational acceleration. In the next video we'll start looking at how we can actually calculate that force that exists between two masses, rather than just measuring it as we might do for this equation that we've seen in this video.